Razafimahatratra. They are both from University of Regina. And they'll talk about the extensions of the Erdős-Ko-Rado theorem. Two intersecting perfect matchings and two intersecting permutations. Let's give it up for now.
Hi everyone, and thank you, Sophia, for your lovely song. So this project is about the Erdős-Ko-Rado theorem for two intersecting families of perfect matchings, and this is a joint work with my supervisor, Karen Moore and Sean Fallett. And I like to start with an example to define a basic concept here. So consider a ground set to be the numbers from 1 to 8, and define the family F to be the family of subsets A1 to A6 as follows. And if we take the intersection of A1 and A2, we will see that it has 5 elements in common, 1, 2, 3, 4, and 5. And if we take, like, for example, A3 and A4, it has 4 elements in common. And in general, if we take the intersection of any 2 of these subsets, we will see that they have at least 4 elements in common, which means that this family is 4 intersecting. So in general, a family F of subsets of a ground set is called intersecting if any 2 subsets here have at least T points in common. And in this definition, if T is equal to 1, it's called intersecting. So this field of study, it's all started with the work of Erdős-Ko-Rado in 1961. And actually they said that if F is an intersecting family of a K subsets of the ground set number 1 to n, then the size of the family has a tight upper bound if n is sufficiently large with respect to k and t. And if the equality holds, then this family of subsets must have a specific structure. So if all of these k subsets has they have a specific T subset of V. Actually, this area is still an interesting area and people are working on it. And here are some of the recent works that are more related to the work I'm doing right now. So in 2005, Moore and Moore proved that the EKR theorem holds for uniform set partitions. And also in 2011, Ellis and others, they proved this, the analog of the EKR theorem for T intersecting families of permutations when the size of the symmetric group is sufficiently large depending on T. And then in 2015, Gotzel and Moore proved that the EKR theorem holds for intersecting families of perfect matchings. And also they conjectured that this theorem holds for T intersecting families of perfect matchings when 2k is greater than or equal to 3 plus 2. More recently, Lindsay proved the asymptotic version of Gotzel and Moore's conjecture when k is sufficiently large with relative to t. And here, our goal is to find the extension of the EKR theorem to 2 intersecting families of perfect matching for all k greater than or equal to 3. Okay, so let's see what is a perfect matching. A matching M in a graph X is a set of edges such that no two edges have a vertex in common. So somehow we are covering all the, and if this matching covers every vertex exactly once, it's called perfect matching. So we are covering every vertex exactly once. So this is called perfect matching. And two perfect matching are called T-intersecting if they have at least T edges in common. So we are looking for the largest possible case when T is 2. And here is the example. Consider the complete graph K8. And here, if we consider the blue edges, they form a perfect matching. So P1, 1, 2, 3, 4, 5, 6, and 7, and 8, it's a perfect matching. And also here, the orange lines are also another perfect matching. And if we overlap these two perfect matching, their union will form these even cycles. And also we can see that here we have two edges that are repeated in both perfect matchings. And also we show their union by this form. So we have a 4 cycle and 2 cycles. And so we show it by 4, 2, 2. And so this is a 2 intersecting perfect matching because we have 2 edges in common. And here, by saying 2k minus 1 double factorial, we mean that we multiply them every other number. So it's like 2k minus 1 times 2k minus 3 and so on. When I was defining the perfect matchings, I forgot to mention that you can define it on any graph, but here we are working with the complete graphs. So throughout this work, we considered the perfect matchings for the complete graph K to K. And so in this case, the number of perfect matching, all possible cases for perfect matchings is 2k minus 1 double factorial. So to continue, we need to review some well-known terminologies. The first definition is the definition of a clique. So a set of vertices that any 2 edges are adjacent is called a clique in graph X. And a co-clique is a set of vertices that no 2 are actually adjacent. Usually we show the size of the largest clique by Wx and the size of the largest co-clique by alpha of x. And here, the adjacency matrix AX actually refer to a matrix which rows and columns are indexed by the vertices. And the ij entry is 1 if I is adjacent to j and 0 otherwise. And similarly, we can define a weighted adjacency matrix for a graph. And it's a symmetric matrix, again, where rows and columns are indexed by the vertices, and the ij entry may be non-zero if I is adjacent to j, or actually if they're on the diagonal, or 0 otherwise, and 0 otherwise. Throughout this work, when we refer to the eigenvalues of a graph, we mean the eigenvalues of its adjacency matrix or weighted adjacency matrix. In general, finding the largest co-clique of a graph is a famous NP-hard problem. So if you want to find the alpha of x, it's like an NP-hard problem. But there is a famous bound for the alpha of x, and here's the bound. So the Detzold-Hoffman bound, or actually the ratio bound, says that if A is a weighted adjacency matrix for a graph X on a vertex set V of X, then if we consider D to be the constant row sum, or actually the largest eigenvalue, and if tau is the least eigenvalue, then the size of the largest co-clique is bounded as follows. So here, as we see, this bound is related to the ratio between K and T here. By K, sorry, I meant D. So it's D over tau. That's why it's also called ratio. And if equality holds for some co-clique S, and if we consider V of S the characteristic vector of the co-clique S, then Vs minus the size of S over the size of vertices times all one vectors is an eigenvector with eigenvalue tau. Okay, now why I want to say why I mentioned the ratio bound. Why do we need it here? Actually, if we go back to our main problem, which was finding the largest set of two intersecting perfect matchings, we can convert it to another problem, which is finding the largest co-clique of a specific graph. So we will define a specific graph, and finding the largest co-clique of that specific graph is equivalent to finding the largest set of two intersecting perfect matching. And actually, this is the graph I'm talking about. So let MT2K to be a graph whose vertices are perfect matchings of the complete graph K2K, and two perfect matching here are adjacent if they're at most T minus 1 intersecting. Here we are dealing with two intersecting perfect matching, so we are working with M2K. So we said that this, the number of perfect matchings is 2K minus 1 double factorial. So this graph has 2K minus 1 double factorial vertices, and two vertices here are adjacent if they are at most 1 intersecting. Here is an example for the case when T is 1 and 2K is equal to 6. So here we have 15 perfect matchings, and two perfect matchings are adjacent. Like if here we consider this perfect matching 1, 2, 3, 4, 5, 6, and we also consider 1, 3, 2, 6, and 4, 6. Sorry, it must be 2, 5, and then 4, 6. Then we will see that these two they don't have any edges in common, so it's they're adjacent. Okay, so as I said, two vertices are adjacent here if they're not intersecting, because T is equal to 1. And actually, Karen conjectured that the maximum co-clique has size of 2K minus 2T minus 1 double factorial for all perfect matchings with T edges in common when 2K is greater than or equal to 3T plus 2. And so for M22K, a maximum co-clique has a size 2K minus 5 double factorial for all 2K greater than 8. So this is what we want to prove. As I said before, using the ratio bound, we can convert our problem into finding the smallest eigenvalue of M22K. So it's enough to find the smallest eigenvalue of the M22K and show that the ratio bound holds with equality for this graph. Actually, this has been done for T equal to 1 by Gotzen and Marr. And here is, okay, and here is what we're gonna do. So if we overlap two perfect matching, we will get even cycles as I showed in the first example. And so if we consider all the even partitions, like if we consider an even partition lambda, then we can define a matrix on it called A lambda, where rows and columns are indexed by perfect matchings. And the entry Mn is 1 if the union of perfect matchings M and N gives us the even partition lambda and 0 otherwise. Actually, if we build these matrices for all possible even cycles, then these matrices form a symmetric association scheme called perfect matching association scheme. And the complex linear combination of these matrices actually form a useful algebra, which is called Bose-Mesnon algebra. And here, if we go back to our graph, now I want to consider this graph in this association scheme. Okay, for the matrix A lambda, we define the graph X lambda, so that A lambda is actually its adjacency matrix. Now, if we consider our graph MT2K, then, or M22K, the union of it's gonna be the union of graphs of the scheme X lambda, in which the even partition lambda has at most one cycle of length 2, and so we can write it as a linear combination of A lambdas. So I can write the adjacency matrix for M22K as a linear combination of A lambdas, for which lambda is an even cycle with at most one cycle of length 2. And so we can show that the eigenvalues of M22K is the sum of the eigenvalues of these matrices. Okay. Actually, in this project, we use two different approaches. For the first approach, we use the concept of different sets and projective planes, and we construct a large co-clique in M22K for 2K equal to 2 to the power A plus 2 when A is a positive integer. And we could show that the ratio bound hold with equality, and so we got what we want, we proved what we need. But here, in this approach, actually we can work with some values of K. As I mentioned, all values 2 to the power A plus 2. And as A increases, this value 2K increase so fast, and it's not easy to calculate, to compute the, and find the clique here. But this actually motivated us for the second approach. So I'm not gonna explain more about the first approach. In this talk, I wanna more talk about the second approach. So the goal here is to find a set of coefficient alpha lambdas for the matrices A lambda. So the matrix M here, which is the linear combination of A lambdas, is a weighted adjacency matrix for the graph M22K, for which the ratio bound holds with equality. So we are looking for a weighted adjacency matrix for our graph, such that the ratio bound holds with equality. Now here, if we have the character table, we can easily find the least eigenvalue of this linear combination, or actually the matrix M, and where we don't have any problem. But the problem is not always the character table exists. Actually, having the whole character table for the perfect matching association scheme is an unsolved problem. And the latest result we have on this table is presented in 2011 by a recursive algorithm to find the character tables up to 2K equal to 40. So for 2K greater than 40, we don't have the whole character table, all eigenvalues here. So what we want to do here, we want to find a portion of this character table. And using this portion, we want to find the degree and the least eigenvalue of M. So by just having this portion, we can find the degree, the greatest and the least eigenvalue of M. and also show that the ratio bound holds with equality. But what we need here to find this part of the character table is the concept of quotient graphs. So we are going to use the quotient graphs to find this, the part of the character table. So in a quotient graph of graph X, vertices are actually blocks of partition of the vertices X, and two blocks B and C, they have, there are like M edges between if the vertex, if any vertex in B is adjacent to exactly M vertices in C. And this is well defined when we have a equitable partition. So why do we need here? Because these quotient graphs preserve some important properties of the main graph X. And one of the most important one is that the eigenvalues of the quotient graph is actually eigenvalue of the big graph. So, for example, here if we consider the graph x 2k minus 2 and 2, then the weighted adjacency matrix of the quotient graph, this graph corresponding to the groups sim 2k minus 4 times sim 4 is going to be this matrix. It's going to be this 3 by 3 matrix, and we can find the eigenvalues of this matrix. Actually, in general, in this project, we calculated 14 different adjacency matrices for classes 2k, 2k minus 2 and 2, and 2k minus 4 and 4, and 2k minus 6 and 6. And we could get part of the character table, as you see here. I just wanted to mention that finding some of this finding some of these quotient graphs was fine, and we could find it like each one in a day, but some of them were not kind to us that much, and some of them took like around a week to calculate just one quotient graph. But anyway, so this is the part of the character table I was talking about. And here our goal is to show that the set of perfect matchings with two fixed edges is a maximum co-clique of the desired type. And to show this, we will determine the appropriate set of coefficients. So we will find our good set of coefficients to build matrix M, for which the degree or the largest eigenvalue is 2k minus 1 times 2k minus 3 minus 1, and the least eigenvalue is -1. So if we put them in the ratio bound, so if we put this d and tau in the ratio bound, then we have the equality, and it's equal to 2k minus 5 double factorial. Okay, here for k between 3 and 9, we defined some weighted adjacency matrix of the graph M22K, for which we can show that the degree and the least eigenvalue are the one that we want. So if we define the following matrices, so for k equal to 3, we define M6 to be A6 plus A4 and 2, and so on. And we can show that what is the least eigenvalue and the greatest eigenvalue here. But how we find these matrices? Actually, we used Gurobi optimizer to find this coefficient, or actually a better way to say that. So for k up to 4d, we have the whole character table, and we based on the character table, we set a system of linear equation, So we set it so that the largest degree is what we want, and the least eigenvalue is -1, and we could find these coefficients. For example, if we consider 2k to be equal to 8 and consider the whole character table here, so here the first 5 rows are the character table. So this is the character table, and the last row I added is the eigenvalues of the M8. So if we compute the linear combination of the first 3 rows with the coefficients we defined, then we will see that these are the eigenvalues of M8, and as we see, the least eigenvalue is -1, and the greatest eigenvalue is 2k minus 1 times 2k minus 3 minus 1. And similarly, we can do this for the rest. And now here, for k greater than or equal to 10, we somehow use some of the eigenvalues in the character table, and we set up a system of linear equation where the equation corresponds to the module to 2k minus 2 and 2, 2k minus 4 and 4, and 2k minus 4 and 2 and 2. And the variable correspond to the classes 2k, 2k minus 2 and 2, and 2k minus 4 and 4. So here is the system I'm talking about. So we set this system, and when we solve this, we will get the coefficient a1, a2, and a3 as follows. And I should mention that this system of equation for k greater than 4 has a unique solution. So this is a unique solution for k greater than 4. And here is the main theorem. So for k greater than 10, if we define the weighted adjacency matrix as follows, with the a1, a2, and a3 that I defined before, then the degree and the least eigenvalue are the ones we are looking for. So we have the ratio bound with equality. So here is the sketch of the proof. I'm not going to go through the whole thing. So for k between 10 and 14, we did the same thing for k less than 10. So we had the whole table, and we just need to check the eigenvalues, the linear equation of the linear combination of the eigenvalues, and we could check it. And for k greater than 15, of course, by looking at the system of the equation we had before, we can see that -1 is an eigenvalue, and also 2k minus 1 times 2k minus 3 is the degree. And now we want to show that every other eigenvalue of m is between these two numbers. So if we consider this set to be the set of our eigenvalues, the spectrum of the m, with mi's to be the multiplicity of the each eigenspace, then we will use the trace of m squared. And we know that the trace of m squared is twice the number of edges, or the degree times the number of vertices in M2. Also, on the other hand, the trace of a matrix is actually the sum of its eigenvalue. So if we use this, we will have this equation. And if we put the information we already have, like we know what is M1, M2, and M3, then we have this inequality for each eigenvalue theta I. So to finish the proof, we will show that actually this inequality, we show that the term in the right-hand side of this inequality is less than or equal to 1. So we are done with the proof. And that's all I wanted to say for today.
Thank you, Mahsa.
Thanks.
So I'm assuming it's Biddy's turn now.
Yep.
Yeah.
So you have
I'm gonna stop sharing.
right, yeah. And then you could share your screen, I think.
Okay, so today I'm going to talk about the two intersecting families of permutations, and there will be a lot of overlap with what Mahsa has done. And this work is a joint work with my supervisor, Karen Marr. So this is the outline of my talk. In the first three sections, I'm gonna define some EKR type problems on permutation groups, and then give some definitions. And then in the last two sections, I'm going to prove some of the things that we did with Karen. So an EKR type theorem for permutation groups. So this is the EKR theorem. It's a very famous theorem, and it was covered earlier by Mahsa. And now we are going to look at an extension of it on the symmetric group. So if you have two permutations, sigma and tau, they are intersecting if they agree on some I in this set. So the symmetric group comes with its natural action on this set. And a family of permutations or a set of permutation in the symmetric group is called intersecting if any two permutations from that set or that family is intersecting. So what Deza and Frankel proved in 1977 was that if you have such an intersecting family in the symmetric group, then its size is at most n-1 factorial. So this is exactly the size of a stabilizer of a point. And in 2004, Cameron and Ku, independently with Lavenuto and Larose and Malvenuto, proved that if this bound is attained by an intersecting family, then the family has to be a coset of a stabilizer of a point. So that means F has to be of the form Vij, which consists of all the permutations that map I to J for some I and J. So then this is the extension on the symmetric group, but one can also do the same thing on subgroups of the symmetric group. So so we can do it. We can also do it for permutation groups. So so we have a group that comes equipped with an action on the set 1 up to n here. So so these are the definitions that we need. In this case, we also need transitivity. So G is a permutation group of degree n, and it is transitive. So G is said to have the EKR property if the size of an intersecting family is at most the size of G over n, which is exactly the size of a stabilizer of a point, again here because of transitivity. And we say that G has the EKR, the strict EKR property if equality holds only for cosets of a stabilizer of a point. So we study such extremal problem. So given a transitive group, we want to find the size of the largest intersecting family, and then characterize the intersecting families that have the largest size. And so to solve this type of problem, a classical way to do it is a reduction to a graph invariant, and here namely the independent set, and it was covered by Mahsa earlier, but what we need to do here is the derangement graph. So if you are given a transitive group, and so we denote by dg the set of all derangements of G, and because of a famous theorem of Camille-Jordan, dg is non-empty. So so the derangement graph is the Kelly graph of G with connection set D of G. And since D of G here is a union of conjugacy classes, what happens is, so gamma of G is a normal Kelly graph, and it's a union of conjugacy class, so it's invariant by conjugation. So it's a normal Kelly graph, and that gives us some nice property on the eigenvalue. We'll see later that we can write the eigenvalues nicely with the irreducible characters of the group G. And the way the edges of the derangement graph is defined is so that a co-clique or an independent set of gamma of G is an intersecting family of G, and vice versa. So the extremal problem that we want to study earlier is equivalent to finding alpha of gamma G and then characterizing the structure of the co-cliques that have this size later. Okay, so now we give some result. So we have a nice family of transitive groups that have the EKR property, and those are the two transitive groups. So this was proven by Mahsa, Spiga, and Tip in 2015, I think. And a second nice family of groups that do not have transitive groups that do not have the EKR property are groups whose derangement graph is a complete multipartite graph. So this is very easy to see. So if gamma of G is a complete multipartite graph, then one can partition the vertex set of gamma of G into, let's say, k parts like this. And by transitivity, these parts all have the same size. So if we let H be the part that contains the identity, then since the neighborhood of the identity is the derangement, everything outside, so all of these parts are derangement. And if we take the stabilizer of a point, it has to be in this part H, because it intersects with the identity. And in fact, one can prove that this H here is the union of all the stabilizer of a point. So in fact, so H can't be can't have G can't have the EKR property unless this H is 1. So this will become a complete graph in that case. And so what Mahsa, Spiga, and I proved recently is that if you have a transitive group of degree at least 3, then gamma of G is not bipartite. And we even have something stronger if gamma G must contain a triangle in this case. And so the only bipartite derangement graph that we can have is an edge, and that is given to us by the derangement graph of scene 2 with its natural action. Okay, so now we talk about T pointwise and T setwise intersecting permutations. So the definition of intersection that we had earlier, we can extend them to T pointwise and T setwise. So F is called T pointwise intersecting if for any two permutation in F there exist T distinct points such that the two permutations agree on each of these points. And F is called T setwise intersecting if for any two permutations in F they agree on some T subset of N. And N here is the set 1, 2, up to N. So what L is, the result that we have is by Ellis, Fried, Gut, and Pilpel. I think this was covered by Mahsa earlier. So given a T, a natural number, for n large depending on T, if F is an intersecting, a T pointwise intersecting family, then its size is at most n minus T factorial. And equality holds if and only if F is a coset of a pointwise stabilizer of a T subset. And so this is an asymptotic result, but it is also conjectured that for any natural number T and N, where 2T plus 1 is less than N, these two statements should hold, so the bound and the characterization. And Alice extended this result for T-setwise intersecting permutations. So it's almost the same statement other than the bound is T factorial times N minus T factorial. And the families that attain this bound are cosets of a setwise stabilizer of a T subset of N. And this is also an asymptotic result. And it is also conjectured that this actually should work for any T less or equal to N. And for the bound and the characterization should work for anything other than NT equal to 4, 2, and 5, 2. For these two cases, there are some other maximum families that are not coset of a setwise stabilizer of a T subset. So what Karen and I did was we proved these two conjectures when T is equal to 2, the bound of the conjecture, not the characterization. So if F is a 2-pointwise intersecting family, then the size is at most this, n minus 2 factorial. And if it's 2 setwise, then the size is at most 2 times n minus 2 factorial. So, so I'm going to prove now, I'm going to give a sketch of the proof at least for the second theorem, so the one on the 2 setwise. And I'm going to present the tools that we needed first, and then I'm going to give the sketch of the proof. So these are the tools. So what we needed to do was, first of all, use the representation theory on some weighted adjacency matrix. So this is a very famous result in group theory. I think that there is a one-to-one correspondence between partitions or Young diagrams and the irreducible representations of the symmetric group. And in particular, an irreducible CSIM-N submodule is these spec module. So they correspond to partitions of N. And as I explained earlier, we want to reduce the problem to the study of the independence number of some graph, and that graph here in this case is the T derangement graph. So the permutation in SIM-N is called a T derangement if its cycle type does not contain a composition of the integer T. So in our case, T is equal to 2, so it doesn't contain 2 nor 1, 1. And maybe an easier definition is it's a T derangement if it doesn't fix a T subset of 1 up to N. And the T derangement graph is the Kelly graph of the symmetric group with connection set DNT, where DNT is the set of all T derangements. Okay, so we find what we want to do is find some spanning subgraph of gamma N2 that has independence number 2 times n minus 2 factorial. So so to do that, we use a weighted adjacency matrix. So so if we let these be the set, the conjugacy class of T derangements in SIM-N, and we let yi be the Kelly graph of the symmetric group with connection set C lambda I. Then the adjacency matrix of yi is a matrix in the conjugacy class scheme of the symmetric group. And if we take a linear combination of these matrices, then we get a weighted adjacency matrix. And this weighted adjacency matrix corresponds to some spanning subgraph of gamma nt. And what we also needed was the ratio bound, a weighted version of the ratio bound. And so it says that if you have a weighted adjacency matrix whose rows and columns sum to D, and it is related to a graph X, then we have this bound. So the independence number of the graph X is bounded by V of X divided by 1 minus the ratio between the largest eigenvalue, which is D, and the smallest eigenvalue of A, which is tau. And what we also need is to compute how to compute the eigenvalue of the weighted adjacency matrix. And this is a very nice way to compute the eigenvalue of such a matrix. So if we are given a group G with we have these conjugacy classes with these conjugacy classes, and if we take Bi be the adjacency matrix of these Cayley graphs, so these adjacency matrices are matrices in the conjugacy class scheme again. And if we take this linear combination, so this is a weighted adjacency matrix, then we can compute nicely the eigenvalues of P with respect to the irreducible characters of the group G, and it is given by this formula here. And Gi, G1, G2, Gk are representatives of these conjugacy classes C1, C2, and Ck. So now we have all of the tools, and we give a sketch of the proof for the two set-wise intersecting property for the symmetric group. So so what we needed to do was find these weights Wi on the conjugacy class of two derangements, so that we have this weighted adjacency matrix corresponding to some spanning subgraph of gamma n2, and we have the following three properties. So the maximum eigenvalue that we want is n choose 2 minus 1, and it should correspond, it should be given by the irreducible character of the symmetric group that comes from the partition N. So in other words, the trivial character. And the minimum eigenvalue that we want is -1, and it should come from the irreducible character with partition n-1, 1 and n-2, 2. And we want all the other irreducible characters to give eigenvalue in the interval -1 and choose 2 minus 1. And in fact, we all have the eigenvalue in this range, so strictly less than 1 in absolute value. So if we are in this setup, then using the weighted version of the ratio bound, we have that the independence number of y, the spanning subgraph of gamma n2, is less than n factorial divided by 1 minus the ratio between the largest and the least eigenvalue. So n choose 2 minus 1 divided by -1, and when this gives us exactly the bound that we want. And so alpha of y is at most 2 times n minus 2 factorial. And since y is a spanning subgraph of gamma n2, So y can be obtained by removing edges of gamma n2. So the independence number of gamma n2 is less than the independence number of y. So then we have what we wanted. The alpha of gamma n2 is less or equal to 2 times n minus 2 factorial. And so let's go back to the weighted adjacency matrix. So this is the weighted adjacency matrix that we chose. So the conjugacy class that we put weight non-zero on are the conjugacy classes with cycle type n minus 1, 1, n minus 3, 3, and n minus 4, 3, 1. And there's really nothing special that we know about these conjugacy classes other than the fact that when we compute the characters, the irreducible characters on these conjugacy classes, the values are all either 0, 1, or negative 1. And so when we write the eigenvalue equation for the two bullets here, what we have is the first line. This comes from the trivial character. So this is the equation that we have. We want this to be n choose 2 minus 1. The second line is the character of the eigenvalue that corresponds to the character n minus 1, 1. And the third line, the eigenvalue that corresponds to the character n minus 2, 2. So when we solve this equation, then it has infinitely many solutions. And it depends on two parameters that we call S and T here. So in contrast to what Mahsa had earlier, where she had that the solution of her system was unique, we have infinitely many solutions here. And so the eigenvalues of A, if we chose the weight that we have here, depending on S and T, will also depend on S and T. And in fact, what we did was that we found this polytope of R2. So when we take T and S from this polytope, then the weight that we have satisfy all of these three properties. So in fact, we also have infinitely many weighted adjacency matrices that work for this proof here. And so that's the proof for the bound at least, but the characterization we haven't really gone that far on it. But what we could prove is that if S is a maximum co-clique of gamma n2, then the characteristic vector of S is in the subspace. So the subspace, which are in fact eigenspaces that comes from the partition n minus 1, 1, and n minus 2, 2. And the proof for the two pointwise intersecting permutation, so the first theorem, is similar to this, but it's a bit complicated. We had to use 6 conjugacy classes, I think, to get the result. So that's all I wanted to talk about. Thank you.
So do we have any questions for Betty or for Mahsa?
I can ask a question.
Mm-hmm.
Okay. I mean, it's a question for both because I think the answer will be the same. If you both did t equals to 2, if you do t equals to 3, do you think in principle there will be a weighted adjacency matrix? It's just more tedious to write down the matrix? Or does it not work for larger T?
think when I worked on t equal to 3 on the setwise, I think I could find a weighted adjacency matrix that worked. But yes, it's really a lot of calculation. It's very tedious.
Yeah, for me as well, I think the way we did these things, like calculating the quotient graphs and things, I think for t equal to 3, it become a little bit more complicated. I don't say it's impossible, but I think it needs a lot of calculations.
Yeah, thank you. And thank you for the nice talks.
Thanks.
Do we have other questions?
I have a question. I'm just curious, I don't know much about this stuff. So you've been using the ratio bound to get these things. Have you guys ever tried using the inertia bound? I mean, does it apply to these cases with the t equals 2 or 3 or I don't know?
I think I have not tried the inertia bound. You haven't tried that. I don't know about Mahsa.
Yeah, me too. To be honest, I don't know what is that bound, but maybe, yeah, it's a good way. I can check it.
Yeah, sorry. Yeah. No, okay, sorry then. Thanks.
Well, the thing about the inertia bound is that it doesn't give you any information about when equality is met. And so oftentimes that information is used in to characterize the case of equality for Erdős-Ko-Rado. So that's, at least that's the reason why I never considered it really for Erdős-Ko-Rado questions. But I think Chris has something in his algebraic graph theory book about using the inertia bound for Erdős-Ko-Rado for sets. Forget the chapter. But.
Yeah, that's just getting the bound.
Yeah,
You can't get, I don't know how to get the characterization.
Yeah.
Okay, thanks.
Sometimes one can look at the dimensions of the eigenspaces and sometimes they fit and one could think it might work and sometimes the dimensions are just off for the eigenspaces, so one knows that at least the obvious approach of using the dimensions of the eigenspaces for the bound will not work. I mean, that one could check, I guess.
I've been trying very hard to find examples where the inertia bound works, and I haven't found anything. Like I've tried it for all sorts of groups and it never works nicely.
And do you know if the dimensions are so that it might be okay?
Well, with the dimensions for the groups, you take the dimension of the character and you square it. So the numbers are almost always off.
Sorry, Karen. Have you tried, did you try weighting with the inertia bound or just the straightforward inertia bound?
I have tried weighting and the straightforward, but Ferdinand's point is good in that we know what dimension we want the eigenspace to be, but then it's not a square number. And for the groups, the dimension, the eigenvalues, their multiplicities is like a sum of squares. And you can see just from the dimensions of the irreducible representations that it can't work in the ones that I've looked at.
Ah, I see.
Yeah, but I really want it to work.
Of course, one could look at other weightings which are no longer in the algebra, but then one has no idea what to do. So,
Yeah, I agree. Then in this case, it's kind of hopeless.